Imagine for the moment that the ground beneath your feet has never moved, that the earth stands still, unshaken by the supposed chaotic nature of the universe that surrounds us. It might sound like heresy to the modern mind, but the fact is that some of the most precise scientific physical experiments ever conducted have delivered results that support this very idea. We'll look at these experiments that together form a body of evidence that challenges the very foundation of our modern understanding of the cosmos. In the early 19th century, French physicist Dominique Francois Arago conducted a series of groundbreaking experiments. Between 1810 and 1818, Arago set out to investigate the speed of light under different conditions, and his results would provide one of the earliest cracks in the emerging heliocentric orthodoxy. Arago's first major finding came through his attempts to measure the speed of light through various mediums. According to the wave theory of light, which had been gaining traction at the time, the speed of light should vary depending on the medium it travels through. This was confirmed in Arago's experiments. He showed that light moves more slowly in water than in air. But Arago's work raised a deeper question. If light behaves differently in different media, what does this say about the movement of the Earth relative to the ether, the medium through which light waves were thought to propagate? This question took on even greater significance with his second, perhaps more startling, observation. While conducting careful measurements of starlight through his telescope, Arago noticed something perplexing. According to the heliocentric model, the Earth's motion around the Sun should cause the apparent position of stars to shift over the course of a year, a phenomenon known as stellar aberration, first identified by James Bradley in 1725. This shift, if it were truly caused by Earth's orbital velocity, should also require Arago to constantly adjust the focus of his telescope to account for the changing angle of incoming starlight. Yet, despite the Earth supposedly hurtling through space at nearly 30 kilometers per second, Arago found that no such adjustment was necessary. The starlight always reached his lens in precisely the same way, as if the Earth were not moving at all. As one commentator observed, Arago submitted the matter to the test of experiment and concluded that the light coming from any star behaves in all cases of reflection and refraction precisely as it would if the star was situated in the place which it appears to occupy in consequence of aberration, and the Earth were at rest, so that the apparent refraction in a moving prism is equal to the absolute refraction in a fixed prism. This anomaly struck at the heart of the Copernican model, suggesting that either light does not behave as expected when the observer is moving, or that the observer, the Earth itself, is in fact stationary. Arago's findings became a critical piece of evidence for the geocentric view, and was a wake-up call for the scientific community. Was it possible they had been presumptuous in adopting the heliocentric theory as fact? Later, Arago's contemporary, Augustin Jean Fresnel, proposed a hypothesis to explain the puzzling results of Arago's experiments. Fresnel's theory, known as the Fresnel drag hypothesis, suggested that when light passes through a moving medium, the medium itself partially drags the light along with it. This drag effect, Fresnel calculated, would be proportional to the refractive index of the medium, reducing the effective speed difference predicted by the ether model. His equation became a cornerstone for defending the ether concept and a moving Earth in the face of mounting experimental challenges, including Arago's findings. However, the Fresnel drag hypothesis is entirely hypothetical, lacking direct experimental verification even today. It was a mathematical fix designed to preserve the a priori assumption of the heliocentric theory, without any physical mechanism to explain how or why such a drag should exist. Next was the Armand-Fitzhugh 1851 experiment aimed to measure the speed of light in moving water, providing an early test of how light interacts with a medium in motion. In his setup, Fitzhugh split a beam of light, sending one half through stationary water and the other through water flowing in the same direction as the light itself. According to the classical wave theory of light, if the ether was stationary, the light moving with the water should have been dragged fully along with it, significantly increasing its speed. However, Fitzhugh found something quite different. The speed of light did increase in the direction of the water's flow, but only partially, aligning with the so-called Fresnel drag coefficient. This result was taken as support for Fresnel's theory, but it actually posed a deeper problem. While the partial drag effect matched Fresnel's predictions, it did nothing to establish the motion of the Earth. The experiment merely confirmed that the speed of light is influenced by the medium it travels through, not that the Earth itself is in motion. In fact, these results can be comfortably interpreted within a geocentric framework, where the Earth remains stationary and the medium itself is moving within a fixed framework. This subtle but critical detail is often overlooked in modern interpretations of the experiment, which tend to force the data to fit a heliocentric model without acknowledging the simpler geocentric alternative. After these early experiments, in 1871, the well-respected Astronomer Royal of England, George Biddell Airy, conducted another experiment that inadvertently bolstered the geocentric perspective. Airy's goal was to measure the velocity of starlight entering his telescope as it passed through a water-filled lens. If the Earth was moving through space, the starlight should hit the water at an angle, requiring a slight tilt of the telescope to compensate for the drag caused by the Earth's motion. Airy's test, however, resulted in what came to be known as Airy's failure. He found that no adjustment was necessary. The starlight behaved as if the Earth was stationary, suggesting once again that the entire framework of assuming a moving Earth might be flawed. Rather than interpret this as evidence against a moving Earth, mainstream science chose to sidestep this troubling result by attributing the effect to the ether being dragged along with the Earth, an idea later abandoned entirely. Just a decade after Airy's failure, in 1881, American physicist Albert A. Michelson set out to replicate his work due to the inexplicable results, and was funded by Alexander Graham Bell. But it turned out that he only confirmed them. As he stated himself, this conclusion directly contradicts the explanation, which presupposes that the Earth moves. 6 years later came the famous Michelson-Morley experiment, conducted in 1887 by Michelson and Edward W. Morley at what is now Case Western Reserve University. The experiment, which used much more expensive and accurate equipment than before, was designed again to detect the speed of the Earth as it moved through the ether around the Sun. They set up an incredibly precise interferometer, set on a pool of mercury so it could be rotated without any vibration. If the Earth was moving through the ether as it orbited the Sun, the light moving in the direction of the Earth's motion should have taken slightly longer to return than the light moving at right angles to it, due to the added speed of the ether wind. This delay would produce a notable interference pattern when the two beams were recombined. But when Michelson and Morley looked at their results, they found no support for an Earth whizzing through space orbiting the Sun. No significant ether wind to show it. Despite repeating the experiment at different times of year and in various conditions, the results consistently showed that the speed of light remained the same in all directions, effectively disproving the existence of the ether, or so the story goes. But what if ether wasn't the problem, but the assumption that the Earth was moving in the first place? If the Earth is stationary, no ether wind should be detected in an amount that supports an orbiting Earth, and the so-called null result makes perfect sense. As one commentator notes, the problem which now faced science was considerable, for there seemed to be only three alternatives. The first was that the Earth was standing still, which meant scuttling the whole Copernican theory and was unthinkable. The second was that the ether was carried along by the Earth in its passage through space. The third solution was that the ether simply did not exist, which to many 19th century scientists was equivalent to scrapping current views of light, electricity and magnetism and starting again. The consternation and quandary of science at the time is summed up by Adolf Baker in his 1972 book Modern Physics and Anti-Physics. He says, "Always the speed of light was precisely the same. Thus, failure of Michelson-Morley to observe different speeds of light at different times of the year suggested that the Earth must be at rest. It was therefore the preferred frame for measuring absolute motion in space. Yet we have known since Galileo that the Earth is not the centre of the universe. Why should it be at rest in space?" 200 years before these experiments, the debate over the helio and geocentric models of the universe was at its height. It would have been interesting to see if the results had been so surprising back then, and how they would have swayed a truly split opinion. As G.J. Whitrow noted in his book, "It is both amusing and instructive to speculate on what might have happened if such an experiment, Michelson-Morley, could have been performed in the 16th or 17th centuries when men were debating the rival merits of the Copernican and Ptolemaic systems. The result would surely have been interpreted as conclusive evidence for the immobility of the Earth, and therefore as a triumphant vindication of the Ptolemaic system, an irrefutable falsification of the Copernican hypothesis. The moral of this historical fantasy is that it is often dangerous to believe in the absolute verification or falsification of a scientific hypothesis. All judgments of this type are necessarily made in some historical context, which may be drastically modified by the changing perspective of human knowledge. Could it be that the pushback against the experimental support for geocentrism might be metaphysical rather than scientific? In other words, was it a question of philosophical worldview? James A. Coleman, who wrote Relativity for the Layman in 1959, said the following regarding the Michelson-Morley experiment. The easiest explanation was that the Earth was fixed in the ether and that everything else in the universe moved with respect to the Earth and the ether. Such an idea was not considered seriously, since it would mean in effect that our Earth occupied the omnipotent position in the universe, with all the other heavenly bodies paying homage by moving around it. Scientific historian Lincoln Barnett noted similarly, the Michelson-Morley experiment confronted scientists with an embarrassing alternative. On the one hand, they could scrap the ether theory, which had explained so many things about electricity, magnetism and light. Or, if they insisted on retaining the ether, they had to abandon the still more venerable Copernican theory that the Earth is in motion. To many physicists, it seemed almost easier to believe that the Earth stood still than that waves, light waves, electromagnetic waves, could exist without a medium to sustain them. It was a serious dilemma, and one that split scientific thought for a quarter century. Many new hypotheses were advanced and rejected. The experiment was tried again by Morley and by others, with the same conclusion. The apparent velocity of the Earth through the ether was zero. Douglas C. Giancoli wrote in his 1985 book, "This null result was one of the great puzzles of physics at the end of the 19th century. One possibility was that velocity would be zero and no fringe shift would be expected. But this implies that the Earth is somehow a preferred object. Only with respect to the Earth would the speed of light be c as predicted by Maxwell's equations. This is tantamount to assuming that the Earth is the central body of the universe." Next we have the Sagnac experiment, performed in 1913 by the French physicist Georges Sagnac. He built an interferometer similar in principle to Michelson's, but designed to detect the rotational motion of the ether. He spun his apparatus at high speed and found a very clear, predictable shift in the interference pattern, exactly the kind of effect one would expect if light waves are being carried by an ether medium, or in a geocentric framework if the universe is rotating around a stationary Earth. This experiment is particularly powerful because it has since been repeated countless times in modern technologies, including ring laser gyroscopes and fibre optic gyros, all of which rely on this very effect to measure rotation. The results are clear and consistent. Rotational motion is real and measurable, and it does not depend on the movement of the apparatus itself, but on the relative motion between the light path and the surrounding universe. In an effort to measure the so-called Sagnac effect on a much larger scale than ever before, in 1925, Albert Michelson teamed up with Henry Gale to test the rotation of the Earth. They built a massive interferometer in Chicago with a 6.4 kilometer circumference, carefully aligned to detect the rotational speed of the Earth as it supposedly spun on its axis. As with the Michelson-Morley experiment, they detected a tiny but measurable interference shift consistent with a rotational speed of about 15 degrees per hour, the same as the accepted rotation of the Earth. But this same result could be just as easily explained by a stationary Earth, with the rotating universe generating the exact same Coriolis forces required to produce the observed effect, as discussed in the previous episode in this series. After all, as Einstein himself admitted in his 1913 letter to Mach, if the mass of the distant stars rotated around a fixed Earth, the same inertial effects would arise within that shell. The results of Michelson-Gale, then, can be seen as entirely consistent with a geocentric model. The question has to be asked then, if the Michelson-Gale experiment produced the expected results of a rotational movement, why didn't the Michelson-Morley experiment prove an orbiting Earth? Later experiments by Wilhelm C. Röntgen in 1888, Sir Oliver Lodge in 1892, and Lord Rayleigh in 1902, and many more, designed to detect the motion of the Earth through the ether, were similarly unsuccessful. All they could find was an approximate 8 to 10 kilometers per second ether drag consistent with a relative axial rotation between the Earth and the surrounding universe. These experiments stand as powerful evidence that the Earth may in fact be stationary, an idea that flies in the face of everything modern science claims to know. But rather than confront these results head on, the scientific establishment took a different path. In the next episode, we'll explore how a radical shift in thinking transformed the very nature of physics and forever changed the popular understanding of science in general. The scientific method was about to be abandoned, and we started to live in Wonderland, with one aim in view: to save the Copernican model.